Hello class, this is Ms. Riggins with today's video on section 6.4, second fundamental theorem of calculus. As you're watching the video, write down notes about the video, making sure to note down important information, formulas, equations, theorems, and graphs. Feel free to pause, rewind, or replay the video as often as you need. And at the conclusion of watching the video, write down a brief summary about what occurred in the video in your notes, and submit that summary as well as a top question via the online whisk form the day before class. And bring those said notes to class so we can discuss it during the whisk review. All right, let's begin. Previous video, we talked about the first fundamental theorem of calculus, and this video, we're going to talk about the second fundamental theorem of calculus. If you remember, in the most recent video, we talked about some popular indefinite integral forms. And we're going to call those forms, instead of popular, elementary indefinite integrals, i.e. basic integral forms. The integral of the constant function, the integral of the power function, the integral of the exponential function, the integral of the cosine and sine function, and the integral of the basic reciprocal function. And now we're going to look at, and the question came up, how do you determine the integral, indefinite integral of functions that are not part of the elementary indefinite integral group? And we're going to talk about that because it's a very interesting process to do that. Now, if you recall, let's come up with a general function. If you recall this particular function from a VA, f of x is equal to e to the negative x squared. And suppose that big F of x is the antiderivative of little f of x. So that means the first derivative of big F of x is equal to the little f of x, okay? And we're just going to suppose that the antiderivative exists, okay? So if the antiderivative exists, and it's some big function f of x, then to find the definite integral from a to b of e to the negative t squared with respect to t, we know from the first fundamental theorem of calculus that it's going to be big F of b equal to big F of a. So let's change a and b. Instead of being from just any general a and b, let the integral from a to b be from 0 to some value x, okay? And as you can see, in order to evaluate the definite integral, all we have to do is replace a and b with 0 and x. And when we do that, we get f of x minus f of 0 is equal to, from 0 to x, the definite integral of e to the negative t squared dt. Okay. Now let's suppose that big F of 0 is equal to 0. So let's suppose the antiderivative at 0 is equal to 0. So then that means that big F of x can be defined as a function of the definite integral from 0 to x of e to the negative t squared dt. So for each value x, you can compute the function value of big F of x, i.e. the antiderivative of little f of x, by basically evaluating or approximating the definite integral from 0 to x of e to the negative t squared dt. Well, how do we go about doing that for, let's say, some value 2? Well, in this case, since we don't have a general function formula, then this answer that we get is the result of doing an approximation. And how good of an approximation? We define that based off of how many intervals between 0 and 2. We're going to use either the trapezoid rule, the left-hand Riemann sum limit, or the right-hand Riemann sum limit, or any of the strategies that we talked about at the beginning of this unit to determine what the area under the curve is from 0 to 2 of this particular function. And this method, we just did this approximation, we got 0.88208. And this, I can't recall if this was Riemann sum or trapezoid rule or midpoint rule. And so that leaves us to what the fundamental theorem of calculus is all about. So the second fundamental theorem of calculus says if you have a continuous function f on an interval, and if a is any number in that interval, then we can define the antiderivative of f to be defined as, for each value x, the definite integral from a to x of f of t with respect to t, which is what we did in the previous activity. And in order to compute this, we don't have a particular formula for depending on each x value, but we basically do have a way of a numerical approximation using either Riemann sums or trapezoid to be able to determine each function value, which may mean it may take more work to define that, but this is how we construct the antiderivative if it's not one of the popular elementary indefinite integral formulas. Okay, and how do we make that as a proof? If you remember last time, we said that was from 0 to x, and in this case they're saying from a to x, where a is any number that in the interval that the function is continuous on. So let f and h be positive, and let's consider, based on the fundamental theorem, these two relationships. So basically their function values at different points where x and x plus h differ by h. And if I were to subtract these two, then the answer that I would get would be basically the difference between these two definite integrals, which can be described based off our properties earlier of definite integrals, the difference from x to x plus h of f of t. Okay? Graphically, what does that mean? So here we have some function big F of x, and as you can see here, this light blue area is f evaluated at x, and this dark blue area, including the light blue area, is f evaluated at x plus h as far as the definite integral. And when we talk about the difference between the two, we're talking about the difference. This difference can be represented as this area. Okay, and this area is approximately the area of the rectangle of width h and of height f of x, where f is the original function. Okay, so can this area be approximated? Yes, but we can approximate it also by looking at its lower bound and its upper bound. So if we take the left-hand limit, left-hand Riemann sum area, let's say of this one, we're going to use the lowest height of being of m, lowercase m, and then the highest height being of uppercase m, okay, for our Riemann sum in essence. Okay, so that means that the area of this difference at the lowest is going to be f of x it's going to be, in this case, it's going to be h, which is this, times m, lowercase m. And the area of this upper limit, i.e. upper triangle, is going to be found by the product of h times big M. Okay, so somewhere in between is the area that we're looking at, which is this area right here. So let's see what we're talking about algebraically. That the difference of these two functions, the definite integrals, indefinite integrals, is equal to it's sandwiched somewhere in between this lower area rectangle and this upper area rectangle. Okay. Well, let's divide both sides by h, and let's keep going. So since f is continuous, then both m, lowercase m, and big case m approach f of x as h approaches 0, which means that the limit as h approaches 0 of this is actually going to be the area of under the curve of f of x. And this is why we can say that little case of f of x is equal to the derivative of big case of f of x, because this right here is an example of the equation of the tangent line, the slope of the secant line as h approaches 0, which is basically give you the limit of the tangent line slope. Okay, so one more thing before we go. We're going to use the construction theorem for antiderivatives on a very popular function that is known outside of math, but in application like in science and physics and all sorts of kind of stuff. And that function is this function, which is the function, the indefinite integral from 0 to x of sine of t over t dt. And we're going to construct the antiderivative function using this construction theorem that was provided to us from the first fundamental theorem of calculus. So we call sine of t over divided by t, the integral of that, the sine integral. Okay, why? I don't know why. Why not sine t divided by 2t or sine t divided by t squared? I have no idea, but that's not my point. They also refer to it as SI of x, sine of x, SI of x, okay? So why is that important? Let's take a look. We're going to construct a table of values for sine of x using x equals 0, 1, 2, and 3. So we're going to do with this more in class about different approximation methods to evaluate this area under the curve of sine t over t from 0 to 1. But this is the ideally of what we're talking about. To figure each value of sine of x, we actually have to use approximation methods to approximate the area under the curve. And that's what we're going to be doing for the next few days. That's it. Thanks.